Hey everyone, in this video we're going to continue our discussion of the electron transport chain and oxidative phosphorylation by focusing on this key enzyme complex called the ATP synthase complex. So what I've done here is I've redrawn our structures of the inner and outer mitochondrial membrane, and I've kept in our four complexes here of the electron transport chain. And recall that at complex 1, NADH dumps its electrons off and a proton gets pumped into the inner membrane space. FADH2 dumps its electrons off at complex 2. And then as the electrons flow through, ultimately 2 more protons get pumped at complex 3 and 4. So each NADH ultimately is going to pump 3 protons, and each FADH2 is going to pump 2 protons. All right, so ultimately then, it's this proton gradient that is the key to making ATP. And it's going to involve this new enzyme that I've drawn over here, which is embedded in the inner mitochondrial membrane. It contains 2 subunits. This is called the F0 subunit. You can think of this as being a very selective and specific proton channel. So notice there's a hole in the cylinder of this embedded membrane. And that's going to be very specific to allow these protons now to flow back into, in towards the matrix. Again, this is the matrix side. Okay, so if there's a proton gradient, if we have lots of protons out here and very few here, there's essentially now a driving force, it's called the proton motive force, that's going to want to equilibrate those protons and have them come back into the matrix. But the mitochondrial inner membrane is a very well-sealed membrane, and the only places that protons could potentially get back into the matrix are through this F0. Okay, so as these protons now flow back through the F0 and get deposited back into the matrix, what's going to happen is the ATP synthase is going to harness this energy, and it's literally going to make the stalk of this second, called the F1 complex, it's going to make this stalk rotate. So the ATP synthase is a motor protein. And as these H+ ions flow through the F0 complex, it's going to cause a rotation of this head group called the F1 complex. Each of these sections, this is a hexameric molecule, contain an active site where ATP is going to be synthesized. So we're just going to draw the following here. We're going to say ADP is now converted into ATP. As each proton comes through, essentially you get a ratcheting of this head about 60 degrees around for each proton that comes through. And as that happens, an ATP is synthesized. So we can say approximately for every proton that comes through the F0 complex, we get approximately 1 ATP. Now I keep using that word approximately because it turns out the number is a little less than a 1-to-1 ratio. Okay, so this key enzyme then, ATP synthase, is oriented such that it makes the ATP on the matrix side. And again, those protons are flowing through the F0 complex. There's this rotation. Now ultimately, the ATP needs to get out to the cytoplasm. Okay, so there are special transport proteins that can exchange this ATP out into the cytoplasm so it can be used by the cell for energy. Okay, so that basically summarizes the figure that I want you to understand in terms of what's happening with ATP synthase. Let's now just summarize what's going on with our stoichiometry here. So recall each NADH pumps 3 protons. Okay, so call that. And it approximately equals, for every proton that gets pushed back through, we get approximately 1 ATP. It's a little less than that. Turns out it's approximately, this is going to give 2.5 ATP. Back when they were first discussing and discovering this pathway, it seemed like the stoichiometry was a 1-to-1 value where every proton that flew through this complex gave 1 ATP. It's a little bit less than that. So basically, each NADH is going to give rise to approximately 2.5 ATP. Likewise, for each FADH2, That's going to pump approximately 2 protons and result in a little less ATP. It's approximately 1.5 ATP for each F-ADH2 that goes through this process. So on the next slide, what we're then going to do is we're going to summarize the stoichiometry then all the way back from glucose, how many ATP glucose ultimately is going to make. All right, that's it for this slide. Hang on, and I'll summarize those in the next slide. Okay, now to summarize the ATP production going all the way back then to glucose and going through the whole process of the glycolysis, pyruvate dehydrogenase, and Krebs cycle, and then ultimate interaction with electron transport chain and ATP synthase, we can summarize this in the following way. So what I've listed out here now is the ATP that are gained at each step. So back all the way to glycolysis, we have a total of +2 ATP, okay, from the actual process of glycolysis. So we're going to call that a +2 ATP. Now the NADH that are produced in glycolysis, those are called the cytosolic NADHs. In most tissues, those are only going to ultimately give 1.5 moles of ATP, okay? And the reason for that is because these cytosolic NADHs, because they're outside of the matrix, they've lost a little of their reducing power, and they end up interacting with complex 2 in the electron transport chain in most tissues. So if you multiply 2 times 1.5, that gives us a +3 ATP for that step if we're going to use those. Now I will mention in muscle tissue and certain other tissues in the body, there is a separate transport mechanism for these cytosolic NADHs that allows them to behave just as if they were in the matrix, and those would give 2.5 equivalents of ATP. I'm going to list that there, but we're going to put it in parentheses. We're not going to put a pink box around that one. But again, most tissues, these cytosolic NADHs, those can give rise ultimately to 3 ATP. Next, as the pyruvate from glycolysis now enters into the pyruvate dehydrogenase complex and the intermitochondrial membrane, recall that there are 2 NADHs produced at that step because there are 2 pyruvates coming through, and those are now deposited in the matrix. Since each of those matrix NADHs now gives approximately 2.5 ATPs, we just multiply 2 times 2.5, and we get 5 ATP for those. Next, we have the Krebs cycle. Recall we're going to go through 2 turns of that. So we get +2 GTP, 1 per turn, and those are equivalent to +2 ATP over in the far column. Next, 2 turns of the Krebs cycle is going to give a total of 6 NADH. There's 3 produced per cycle. Now we multiply those by 2.5, and now we're getting +15 ATP. So now this is where we really start to rack up a lot of ATP production. It's from all these NADHs that are in the matrix of the mitochondria. Lastly, there were some F-ADH2s that were produced, 1 per turn, and since we're going through 2 turns of the Krebs cycle, we take 2 F-ADH2s times 1.5. Recall these only dump their electrons off at complex 2 and therefore do not pump as many protons, and so that gives us +3. So if we total up in the pink boxes then, the total number of ATP from 1 mole of glucose, we're going to say from 1 mole of glucose. Okay, let's add these all up. So I got 5 and 5, that's 10, plus 15 is 30. I'm sorry, that's not right. 5 and 20, there we go. It's 25 plus 5, that's 30. There we go. I knew my math was right. So 30 ATP are produced for every mole of glucose that's completely oxidized to CO2. Now that's in most tissues, okay? Notice I was using that number there. Now if we're talking about muscle tissue, the muscle has a slightly different pathway that allows these NADHs from the cytoplasm to get into the matrix without losing any of their reducing power. And so you can add on an extra 2. So we're going to say in parentheses 32 ATP. And evolutionarily, that sort of makes sense. Muscle, because of the contraction of the muscle tissue, the actin filaments in there, the actin and myosin filaments, that requires ATP. So it makes sense that in muscle, that there has evolved this additional sort of little burst of energy for every mole of glucose that gets oxidized. But the key number I'd always remember is this one here, 30. Just to mention, in many years ago, again, when they were first going through this pathway, it was thought that these numbers here, instead of 1.5 or 2.5, were actually integers. So back in the old days, back when I was learning this stuff, when you tallied up everything, we got a number of 36 ATP. But it's more recent research has come out to show that under most cellular conditions, these numbers are actually slightly lower than the integer values. And so 30 represents the number of equivalents of ATP from 1 mole of glucose. That's a much more accurate description. All right, so this little summary table is one I definitely would get to know. And then also don't forget that muscle tissue, you get that extra little burst of an additional +2 ATP. All right, so that finishes up everything for electron transport, and then oxidative phosphorylation, and then the discussion of ATP synthase. I hope this helped. Good luck.